Hi, welcome to my channel, JaberTime. Today we're going to talk about the double integrals over rectangles, and we're going to talk about two types, the dx dy or dy dx, as being called type 1, type 2. To get you started, we'll take you back to Riemann sum in 2 dimensions. We take care of partitioning A to B, and then we use the right Riemann sum, left Riemann sum, midpoint, and so on. Finally, we apply the limit and we cover all the area exact. In 3D, my domain here is from A to B and from C to D, which is right there. In 2 dimensions, the domain would be like going from A to B as an interval. Now here, to build up to the surface, not the curve, we need to cover that volume, let's say. To find the exact volume under this surface, on top of this region R or domain, we need to partition it. To partition it, the best way is break it down from A to B to delta x's and from C to D to delta y's. And it would be nice if they're all equal. Then we'll make delta x goes to 0, we'll make delta y goes to 0, and eventually every point inside will apply f of x, y to it to reach up to the surface, and that will be the height. So if we look at one sample, it's like a 2 by 2. You go up. If you go from this point, it looks like because the surface is concave up, you're going to go up above it, and you're going to be overestimate. If you take this point, you're going to hit the graph at earlier point, and once you close it, you're going to be underestimate. Now eventually we're going to apply the limit, so we don't need to slow down. And this is how it's going to look like if you partition it that many times. Estimate the volume of the solid that lies above the square from 0 to 2 to 0, from 0 to 2 on x, and from 0 to 2 on y. And below the elliptic paraboloid, z equals 16x squared minus 2y squared. Divide r into 4 equal squares, because just like the first practice, it would be easier if it's only like 2 or 3 or 4 equal squares. And I was told to use the upper right corners. We don't call it right Riemann sum or left. We have too many options here. So this would be, if you are in region 1, 1, we're gonna use the upper right corner. From this point, we're going to go up and reach the surface and close that. Let's say, in this case, it's going to be called 1 by 1. It's not like a 2 by 2. On this region, this is my upper right corner. As you could see, far end, this point 2, 2, when you go up, it's going to be shorter than the others because that's a paraboloid. If you look at it, it's z equals 16 minus x to the second minus 2y to the second. Just focusing on minus x to the second, it's a parabola that opens down going with the x-axis. And this one will be another parabola going down narrower going with the y. And the 16 will tell you that you are shifted up 16 units, as you could see. So that explains the base where we build those bars, and that is a little bit more. So this is the region 1, 1. We're gonna apply F11 just by plugging in 1 here and 1 here, and end up with 13. Region R1, 2, you plug in 1, 2, 1 here and 2 here, you get 7. If you take care of those two, they are listed for you right here. Now, the area of each square is 1 unit, because we're taking m and n to be 2, they're equal, and we're dividing it as they told me to 4 equal squares. So each square right here will be 1 by 1, a 1 unit area. The volume will be approximated to the summation of f of xy. That's like f of this point, f of this point, f of this point. That's what this means. The heights, this would be like the base times the height, base times the height. And the base is delta A, which is 1, to make it easier on us. Where j on the y changes from 1 to 2, from here to here. That will be the whole work. The volume of this bar right here will be delta A times f of 1, 1. F12, that's this one here, region 1, 2, will be the base, which is 1, times the height, which is f of 1, 2. Same thing applies for the rest. Delta A is 1, delta A is 1, delta A is 1, and the outputs are written on the side for us. Just plug them in and finish it with 34. Now, of course, if you partition this more than 2 by 2, like 2 units here and 2 units right here, to 4 regions, you're going to be more accurate. Because look at it. We're losing that much, we're losing that much, and that much, and that much right here. Now, if you partition it more, where m and n equals 4, not 2, you get this picture. Go by 8, I get this picture. Look at the volume. It's 41.5, and the one before was what, 34? Now it's 41.5, 44.875, 46.46875. That's more accurate. And when you apply the limit, it's just gonna cover it all 100%. Now, if r equals xy such that x is between -1 and 1 and y is between -2 and 2, evaluate the integral, which is a square root. Well, it says here evaluate. It doesn't say estimate. And we did not learn how to evaluate or integrate first, double. But that's how we do it also in calculus 1, to support the concept of what is the integral. So to do this, you need to understand the graph. Because without graphs in double integral and triple integral later on, it's hard to move on and put your limits on the integrals. Let's take a look. First of all, this is my z value. It's a square root of 1 minus x squared. But that cannot be negative. So now I know that my z, or my surface, is above the xy plane. Also, if you simplify this or rewrite it differently, it's like x squared plus z squared equals 1. That's a cylinder, because we're in 3D. Going with x and z, and y is loose, so y changes, so we are going with y centered at the origin, but we're going with y. Y could be 1, could be 2, could be 3, and so on. So it's a circle, if you look at it from one point of view, with the radius of 1, and if you include the y value, it's going to be a cylinder. But of course, we have to be above the xy plane. So we have the restrictions. X has to be from -1 to 1, including, and y has to be from -2 to 2, because they told me right there. And that is the graph. It's a cylinder, but I was told, or here it shows that we have to be greater than or equal to 0, so above the xy plane, and y goes from -2 to 2, that's the y value, and x has to go from -1 to 1, which agrees with the cylinder. Because they want me to evaluate, I need to find the volume here. To find the volume, we don't know how to integrate this. So we're going to do the following. We're going to do the base as if this is a base times the height. The base right here is half a circle, half pi r squared, which ends up as pi over 2, times the height, which is 4. So when you do that, pi over 2 times 4 simplifies to 2 pi. Iterated integrals, repeated integrals in other words, one after the other. So when you have a double integral, you take care of the inside first, then you go outside. That's one way to say it. So we could take care of dy first, going from c to d. Once we're done, we apply the outer one from a to b dx. The inside part becomes a of x, a function of x, that you could go after and differentiate with respect to x. There is more meanings into this. If it's too hard, you could skip it and just like apply the examples. But it does make a lot of sense, because when you find the volume for a room, sometimes we call it base times height or length times width times height. But think about it as base times height. The base is like the floor, the surface of the tiles. And when you bring it all the way up, covering all the height from the floor to 7 feet, that means you're covering the volume. So now you're kind of like taking a slice or the base and covering all the height. That same thing applies here. So to find the volume here, it's almost like I want to say like, let me find this base and I want to go this height. But the base is a function because it's under the surface and it changes. That is a function of x. Because once you do it, it's a function of x, then you apply from a to b. Take it with y first. Take it with y. Y changes. You slice it this way. And you go from c to d. And you find that a of x. Now a of x, when you go from a to b, with respect to x, you are covering all the way, all the slices from here, 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 all the way. And that should do it. So a of x is the inside part. If we integrate the function a with respect to x from x equals a to x equals b, we get a to b ax dx, which is what was mentioned earlier. On the other hand, differently speaking, we could say, let's find from a to b first. Then we'll apply dy. And that is what we have. So once you take care of this, from a to b, you're going to find a slice like this. Then the integration with y, you're going to go back and forth. If you call it that way, of course we don't go back and forth. But imagine if you take this slice and you go right and left, you will cover the whole volume. It's like, as I said, in a room, base times height. This is like my base, and this is my height. We're going to start here, and we're going to multiply it. Now, let's see some practical examples. Evaluate the double integral from 0 to 3 and from 1 to 2 x squared y dy dx. Well, of course, if this is dx, that means this is x1 and this is x2. If this is dy, the inner part will be y1 and y2. Let's take care of it step by step. Here's my function. I'm circling the inside part. Let's take care of the inside part first. When we do it with dy, we treat x as a constant. The integration of x squared y treating x as a constant will give me x squared stays the same. Y becomes y to the second over 2. And we're going from y1 to y2 because that's my y. Apply the 2 and the 1 and simplify. I get 3 over 2x to the second. Now this is the inner part. Let's go back to the problem. The problem was from 0 to 3 dx of this much, which we found right here. From 0 to 3 dx of what we found earlier. We know how to finish this. Apply the 0 and 3, and I end up with 27 over 2. Let's do it the other way around. Now if you notice, I have the y out and the dx first inside. Of course, dx goes from 0 to 3, and dy goes from 1 to 2. dy goes from 1 to 2. They go together. So if you switch the dx and dy, you have to be careful about the limits too on the integrals. Let's work inside. Same idea. Treating y as a constant because my variable is x. That's how we integrate. Y is a constant. X to the second becomes x to the third over 3. We go from x equals 0 to x equals 3. Do the math. Simplify and get 9y. Same idea. Let's go back to the problem because that's not the problem. That's part of the problem. When you go back to the problem, we're going to apply from 1 to 2 dy as an integral to what we found here, which is 9y. Now integrate with respect to y. Plug in 1 and 2 for y. We also get 27 over 2. Now, here's another method that works sometimes, not all the time. You could split them. You could take the x's on side and the y's on side and make it a product. I could do it here because I can. Sometimes you have like x squared minus y to the third. You can't split them. They have to be factors. Okay, that's one idea. Also, if they are not attached together, that I cannot separate them. Like you can't separate, let's say, square root of xy. No, square root of x times e to the power x over y. When it's too complicated, you cannot break them down. So when you can, like this one, you can do it if you want. So x to the second becomes x to the third over 3 because we are integrating with respect to x. This one we know how to do it. I don't want to read it. I just want to save you some time. Do the math, plug in the numbers, simplify, and it will give you the same answer. 9 times 3 over 2 is 27 over 2. Now, let's take another example. Double integral over region R, where R is defined to be from 0 to 2 on x and 1 to 2 on y. First method, integrate with delta y first. Take care of that first. Treat x as a constant. So x like a 5 will be 5y. As you can see, xy. Y is my variable. Y to the second over 3 by 3 cancels. Plug in 1 for y, plug in 2 for y and subtract. And I get x minus 2. Let's go back to the problem. Now this x minus 7, I think I said x minus 2. X minus 7 will go right here instead of this whole thing. And we integrate with respect to x from 0 to 2. And I have the following. Plug in 2 and 0. Simplify, we have negative 12. Let's do it the other way around. Notice this one here before I do it. I don't want to forget. You can't split those two. They're not factors. You cannot do it like a third way. So you just have to be aware of that and be careful. Let's do it the other way around. Look, dy is outside, 1 and 2 is outside. dy was inside, 1 and 2 was inside. We do this first. We come back to the problem. We know how to integrate, treating y as a constant because x is my variable. X is my variable. X becomes x squared over 2. 3y to the second acts like a constant for me. So it becomes minus 3y to the second times x. Or you could write the x inside. Plug in the values. Simplify. I have 2 minus 6y to the second. Let's go back to the problem. Now integrate with respect to y from 1 to 2. And when you simplify, you should get the same answer. And that should do it. It's about 22 minutes. Trying my best not to make it 30 or over 30 minutes. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.